In this tutorial, we'll explore an algorithm called random forests. A random forest is basically a collection of decision trees. A random forest is widely used for both classification and regression. Random forests are a way to do machine learning so that you can use the results from data that you have to predict the results of something that you don't know. This is true for all machine learning. So with random forests, we use past data to make predictions of unseen data. Random forest is a bit of a Swiss Army knife of machine learning algorithms. It can be applied to a wide range of problems, and it's fairly good at all of them. So, what is a random forest? Random forest is simply a collection of decision trees that have been generated using a random subset of data. The name random forest comes from combining the randomness that is used to pick the subset of data with having a bunch of decision trees, hence a forest. In order to understand a random forest, you have to understand a decision tree. So a decision tree is simply a step-by-step process to go through to decide a category something belongs to. For example, let's say you are watching a bunch of vehicles traveling on a road and you are teaching a child who has never seen the different types of vehicles before how to tell them apart. You could make a bunch of questions to go through to determine what type of vehicle something is. Is it tall? Is it heavy? Does it have more than 4 wheels? Then you can classify it as a bus. A chart of this simple decision tree is shown here. To use the decision tree, you start at the top and begin hitting each decision in series. At each point, you need to make a choice on which way to go between exactly 2 options. Eventually, you reach the bottom and have a decision as the outcome. In this case, what type of vehicle something is. If your decision tree is good, you can now pick up an unknown vehicle and follow the chart to classify the unknown vehicle. A random forest is made up of a number of decision trees, each of which has been generated slightly differently. So take a look at this chart, which contains a random forest with a bunch of decision trees. In order to generate those decision trees, you need a starting dataset. That starting dataset needs to have both features and labels. Labels are the final answer that you get when you're trying to categorize something. In this example, labels would be if the vehicle was a truck, plane or train, car or taxi. You need a set of data where you know the results to start with, so you can use that to generate the decision tree. The other important part of your starting data set are the features. Features are information about the item that you can use to distinguish different results from each other. So in this example, we have features such as the height, the color, the width, how easy it is to park, does it have wings, etc. When you pass the dataset with both features and results into the random forest generation algorithm, it will examine the features and determine which ones to use to generate the best decision tree. Pause and take a look at this table and familiarize yourself with how the data is structured. So essentially we have about 1000 instances. So these are our data points. And then we have features. So each data point represents a specific vehicle. So for example, the first instance, this vehicle had a length of 4 meters with a height of 1.2 meters, did not have wings, it was easy to park, its color was white, it didn't need tracks to travel, it had 4 wheels with 4 seats, and it's been classified as a car. So this is how the data is structured. So let's say we want to create a chart, and let's take a look at the length and height columns and make a chart to see how it looks. So in this plot, cars are red diamonds, taxis are orange squares, trains are yellow triangles, and planes are blue circles. So on our x-axis we have the length, in meters, and on the y-axis we have the height of a vehicle in meters again. If we gave this vehicle classification problem to a person instead of an algorithm, how would they do it? Well, the first thing to do is separate the trains. Everything else is more or less than 1,500 meters. But the trains are long, which make them the low-hanging fruit of this problem. So we can draw a line between the trains and the other vehicles and say that anything on one side is a train and anything on the other side is one of the other vehicles, which we will figure out later. With a single line, we've classified one category. Now that the trains are separated out, how about the rest of the vehicles? Well, they're more challenging, but we can still make some judgment calls that are better than simply guessing between the remaining vehicles. To start with, most of the planes appear to be taller than either cars or taxis. So we can draw a line and say that anything larger than 4 meters in height and more than 15 meters in length is a plane. What we see is that we were able to split off most of the planes, but not all of them. There are a few planes that are smaller than our cutoff lines. If we had made our cutoff line smaller, then we would have started to pick up cars or taxis and classify them as planes. So it might not be possible to always tell the difference between the cars and planes just by the length and height. We may need to use some other features. Intuitively, this makes sense. Even in real life, it isn't always easy to tell the difference between a very big car and a very small plane. So based on this data, we might say that the really small vehicles are always taxis, the kind of small vehicles are cars, and the largest vehicles are taxis again. We could create a chart that looks like this, with portions colored to represent the category. Note here that there is a section where we are unable to differentiate between cars and taxis. Some cars are more than 2.5 meters in height and some are less. And some taxis are also more than 2.5 meters and some are less. So same applies to the length as well. So at this point, we'd probably give up trying to classify whether a vehicle is a taxi or car based on height and length. This is because we're doing this manually. Now the algorithm, the single decision tree algorithm, wouldn't give up. It will go on classifying each data point until it can find whether it's a car or a taxi. What we looked at is a manually generated tree. So now let's look at a computer generated decision tree, and that's plotted below. So at a high level, this plot is very similar to the one that we generated manually. There are some differences though. Look at how the decision tree chose to split off the trains. So we did it with a single diagonal line. The decision tree used two lines, one horizontal and one vertical. The decision tree works by picking a criteria and a threshold. The criteria specifies what to split, for instance, length or width, and one single criteria is always used. The threshold specifies where to split, that is, what value to split at. Remember, we use random forest extensively in machine learning, but not one big decision tree. A random forest is a collection of decision trees. So why do we not use one big decision tree? Well, when we created the decision tree manually, remember eventually we got to a point where we gave up classifying the data. We recognized that the large grouping of owner cars and taxis was essentially random because we could have taxis that were lengthier or cars that were lengthier or taxis that were taller and cars that were taller or lesser. So trying to separate everything would not be useful because it's truly random in terms of height and length. The computer does not throw up its hands and stop. By default, it continues until every single piece of data is split into a category that is 100% pure. Let's zoom in on this portion to see how the data is split. Zooming in on the decision tree, we can see This leads to incredibly fine distinctions in how an area is categorized. This is an example of overfitting. Overfitting means that we are drawing too fine a conclusion from the data that we have. The whole purpose of making this classifier is that when we get a new vehicle, we can measure the height and length and know what type of vehicle it is. However, the new vehicle will be all a little different than the data that we already have. So trying to say that a vehicle with a width of 2.7 meters is a car, but the one that has a width of 2.75 meters is a taxi is not really very correct. This is an example of overfitting. A single big decision tree suffers from this problem of overfitting. To understand what this means, we need to know what bias and variance are. So let's take a look at bias and variance. Many metrics can be used to measure whether or not a program is learning to perform its task more effectively. For supervised learning problems, many performance metrics measure the amount of prediction error. There are two fundamental causes of prediction error: a model's bias and its variance. A single big decision tree tends to be low bias and high variance. What does this exactly mean? Assume that you have many training sets that are all unique, but equally representative of the population. A model with high bias will produce similar errors for an input regardless of the training set it used to learn. Bias refers to how far away is a prediction from the actual value. Let's say we split our data into 3 training sets and we created a decision tree and we trained our decision tree on each of the sets to compare the outcome. So if we were to predict using the 3 sets, let's assume that all 3 sets predicted the outcome to be a truck. But in reality, the actual was a car. Now we notice here that the prediction is different from the actuals. So this is an example of what we call as high bias. So even though the data sets, we have 3 data sets and 3 of the data sets predicted it to be a truck, but in reality it was a car. So this is an example of high bias. The predicted and the actuals vary, and it's a result of high bias. A model with high bias will produce similar errors for an input regardless of the training set it used to learn. Conversely, a model with high variance will produce different errors for an input depending on the training set that it used to learn. For example, the model predicted a truck with the first set of data, and then it predicted a car with the second training set, and then it predicted a plane with the third training set. So notice here that out of all the 3 predictions, it correctly predicted once with the second training set. So depending on which training set is used, the prediction could vary, and that's why this model has high variance. A model with high bias is inflexible, but a model with high variance may be so flexible that it models the noise in the training set. That is, a model with high variance overfits the training data, while the model with high bias underfits the training data. Let's explore this concepts of bias and variance through the dart throwing example. So each dart is analogous to a prediction and is thrown by a model trained on a different dataset every time. So a model with high bias but low variance will throw darts that will be tightly clustered but could be far from the bullseye. The close cluster in a high bias low variance means it's low variance. A model with high bias and high variance will throw darts all over the board. The darts are far from the bullseye and from each other as well. A model with low bias and high variance will throw darts that could be poorly clustered but close to the bullseye. And finally, a model with low bias and low variance will throw darts that are tightly clustered around the bullseye. So ideally, a model will have both low variance and low bias, and this is our final goal. But efforts to decrease one will frequently increase the other. So this is known as bias variance trade-off. Now to fix this is where random forests come in. So random forest tends to address this issue of bias and variance the way it works. So let's take a look at how exactly it does that. It's important to note that a single tree is prone to low bias and high variance. A random forest solves this because it uses a collection of trees. So make a note about the difference between using a single tree to make predictions versus using a collection of trees to make predictions. So the problems of variance and bias are usually on a single tree, whereas a random forest fixes a lot of these problems associated with bias and variance. If you're trying to tell the difference between cars and taxis based on their size, a decision tree might break down the data into very small specialized ranges that work for your data but not for any random vehicle that might come in. So random forest attempts to fix this problem by using multiple decision trees and averaging the results or taking a vote. Example, let's say we generated 3 decision trees using slightly different sets of data. For a new instance, we run it through the 3 trees. Then the results for each of the decision trees are combined. So if multiple decision trees are giving you different results, which should you choose? Random forest solves this problem with voting. There are 2 different ways the voting can work. The first is to just count all the votes by all the decision trees and take the highest count as the solution. The other way is to count all the votes and return a result based on the ratio of the votes. Because the decision trees are built with different data, they will not all be the same. This is one area of the randomness in a random forest. When generating each tree, that tree has a unique set of data. That set is generated from a random subset of all the available data with replacement. This technique is known as bootstrap or bootstrap aggregating or bagging. Each of the trees uses a set of data that is the same size of the original set. As an example, let's say that you're generating a tree from the set of numbers from 1 to 10. The original dataset has 10 numbers, so the new tree will have 10 numbers in it as well. The original dataset has numbers only from the range of 1 to 10. So the new tree will also have numbers in the range of 1 to 10. However, the original dataset has all of the numbers 1 to 10. The new tree will probably only have some of them. For instance, a tree might be 1, 2, 2, 3, 5, 7, 7, 9, 9. This was generated by picking 10 numbers out of the set 1 to 10 with replacement. That is, once a number was picked, it could be picked again. If you generated another tree, it might be 2, 3, 3, 5, 6, 6, 7, 7, 8, 9. This tree will be similar to the first tree that was created since they use the same pool of data, but they will not be the same. For instance, this tree includes 8 in its set and omits 1. Both trees still omit 10 just by luck of the draw. Since most random forests contain anywhere from a few dozen to several hundred trees, then you're likely that each piece of data is included in at least some of the trees. So how does this translate to real data? Take a look at this table here. So we have the original data of the background. which has 1000 instances. So out of the 1000 instances, we are going to create 2 subsets, and each subset also has 1000 instances. But take a look at the number of the instance. See, for example, in the first subset of our data, we have instance 5, 2, 3, etc. In the second instance, we have instance number 17, 7, 3, etc. So you end up with unique sets of data in both. It's different data with replacement. That means a data instance can be put back into the original set and then used again. So this is how we create multiple training sets, and we're going to train our trees on these multiple training sets. So you're going to end up with different decision trees using different data points. The other way that a random forest adds randomness to a decision tree is deciding which feature to split the tree on. The way that random forest deals with this is to not let the trees look at all of the features. So at any given branch in a decision tree, only a subset of the features are available for it to classify on. Other branches, even higher or lower branches on the same tree, will have different features that they can classify on. So in this example, we have 5 different trees with different combinations of features on which the outcome is being predicted. So for example, the first one is lengthy on the first branch, and then it's checking for whether it has wings. So similarly, we have other trees. Each one has a different set of features on which it's classifying the incoming data. So how do we make predictions in a random forest? So let's say we have an unknown vehicle. So we're trying to predict what type of vehicle this is, and we have some data about this vehicle. So for example, the length of this vehicle is 5 meters, height is 1.2 meters, easy to park is classified as yes, does not have wings, has seating of 5, and the color is white. So how do we now apply the random forest to classify what type of vehicle this is? So essentially, you would take this data and feed it into each of the trees. For example, the first tree will evaluate, is it lengthy? So in this case, since it's a length of 5 meters, we say no. So the first tree gives us an outcome of this vehicle being a car. Now the second tree, where it asks the question, easy to park, and in our case the data says it is yes, and then it will evaluate, is it lengthy? And when it sees that it's no, it classifies it as a car. Now for seating, it looks at, does it have seating? And in this case, where it says no, it's evaluated to be a truck. And if it's yes, then it's further evaluating whether it has wings or not. Now notice here that does it have wings, it gets classified as no or yes. In this case, since our data point does not have wings, it's getting classified as a train. That's alright. Now let's look at the next tree, where it's looking for color. So in this case, the color is not yellow, so it gets classified as a car. And finally, it looks at is lengthy, and since it's not lengthy, it gets classified as a car. So we have different trees here giving us an outcome, and out of the 5 trees, we realize that 4 trees classified it as a car and 1 tree classified it as a train. So essentially, if we go with the voting mechanism, this particular vehicle will get classified as a car. So we are predicting that this vehicle is a car. Random forests are part of something called ensemble learning models. Ensemble is a combination of estimators or classifiers that performs better than each of its individual classifiers. So for example, if we are trying to predict the housing price, our different trees could be giving us different results or different predictions for the housing price. So we normally would take an average to figure out what's the housing price. So notice here that we've used 3 different classifiers to get to outcome, and we're combining all of them to get a result. So this is called an ensemble. We could also use different algorithms and take a vote. So in the earlier example, all of the classifiers were decision trees, but we could have used different models as well. Suppose you've trained a few classifiers, each one achieving about 80% accuracy. So let's say you may have a logistic regression classifier, a random forest classifier, a k-nearest neighbor classifier, or even an SVM, which is support vector machine classifier, and perhaps a few more. So we could combine the results of all of these classifiers to get the final outcome. So a very simple way to create an even better classifier is to aggregate the predictions of each classifier and predict the class that gets the most votes. This majority vote classifier is called hard voting. So this is part of the